third part and the last lecture of Guilherme that will talk us about compact objects and how to model them. Please go ahead, Guilherme.
Okay, can you hear me? Is this working? I guess so. So, thank you and hello everyone again. So today will be the final lecture of this, well, my course. It will be the shortest of them, but first and foremost, let's just sort of review what we've seen so far. So 2 days ago, in the part 1, we basically sort of introduced this notion of compact objects and what are the compact objects that we currently know that exist in our universe. And, well, one of them was, of course, black holes, as you are all aware of. Then we've talked about a bit about neutron stars and also white dwarfs, although in the definition that I provided, white dwarfs are not really what I called compact objects. And then we were sort of studying and understanding how can we model this type of compact objects with a fluid description of matter. This is just related with what Miguel was just showing about the TOV equations. And I'm also going to show this hopefully now. And after this, of course, we need to talk about the equation of state, and that's what we did. So equation of state, just to recap, is the missing piece of information that we need to describe the state of matter, because otherwise we are just saying that it's a fluid, but there are a lot of types of fluids. You need to really be concrete and say what is the microphysics of that fluid, and that is the role of the equation of state. And there are many types of equations of state. We've seen the constant density that sort of leads to the Book-Dahl limit and the Book-Dahl result. And then there are the other ones that you typically use to model stars, for example, polytropes, and also models with constant sound speed that sometimes have applications to model quark stars and to do some interesting analytical results. Okay, this was in part 1. In part 2, we were basically studying again this aspect of compact objects, and I've introduced what are these exotic compact objects that you can think about like anything that is not a neutron star or a black hole. And yeah, I'm motivated a bit. Why do we care about this line of research? Of course, one of the perspectives is, well, if we don't study them, we will never be able to see them, because these are very compact objects. We need to understand what is the phenomenology of these objects, and this is something that I'm going to talk about today. But also they are important in order to validate the black hole hypothesis. Now, one thing that we did yesterday was to understand how can we construct these different models of exotic compact objects, and I've mentioned a bit of these artificial models. I mean artificial in the sense that we sort of don't have any higher motivation on how they can be formed, that I've mentioned, like wormholes and gravastars. But I should emphasize that, again, although I'm calling artificial, I don't mean that we should not study them. They are very useful, as you'll see actually in a few slides. And also we introduced these two objects, which are anisotropic stars and elastic stars, which are sort of motivated by anisotropic states of matter. And of course, besides these, there's also, well, a lot of other objects, like the boson stars that have been quite talked about in this workshop. So, and to recap for the people that were not here yesterday, basically both anisotropic stars and elastic stars are obtained by solving a similar system to what Miguel was just sort of solving in the computer, the TOV equations, but these are sort of an additional variation, which is the anisotropic TOV equations. For anisotropic stars, I want to emphasize there are a few problems. Well, one of them is that you need to prescribe an additional equation of state, and I recall that one equation of state is bad enough, but two equations of state is really a mess. While for elastic stars, you actually only need one equation of state. This because it starts from a Lagrangian approach, and all the pressures are actually given in terms of the density, so you only need to specify what is the density. And I don't know if I mentioned this yesterday about these elastic stars, but another good thing is that all the formalism does not really require that you are in spherical symmetry or or in, well, static spacetimes. Actually, this can be generalized to well, other symmetries is something that I'm doing, but is, of course, as always, much more difficult. And in both cases, the key feature is that, well, you can, in principle, construct physically viable ultra-compact objects, so objects that have a light wing outside. There are more, of course, interesting things, but I just want to highlight this one here. And so, let me show you actually how to do it in practice. So I'm going to open my Mathematica notebook that I will afterwards share with all of you, just to show you that, well, this is a bit more than just talking. It's actually, well, you can run it in your Mathematica notebook in just a couple of lines, and it will be very easy. So let me see if I can, well, show this here. So I'm going to put this now, and I'll be in silence for a bit. Yeah, sometimes when I'm here, okay. So this is sort of the notebook that I will share with you. So again, this is a very simple Mathematica notebook to integrate the TOV equations. So this first, well, how can I scroll? This first piece of the Mathematica code. Okay, is the size of the letters good enough for you to see? Okay. So this is, well, just some, well, one of these modules for putting the units in the units that I like, which are solar mass units. You don't really care about this part here, so I'm going to close it. And then let's go to the field equation. So this is sort of what I've been introducing. We'll start with fluids for now, right? So the type of equations that we want are the TOV equations, which are these ones that I write here in LaTeX form, of course. And well, if it's for fluids, the only equation, well, are basically these equations here, with the exception of this last term in the last equation, which is 0. These are the anisotropic stars. But, well, since this is just putting this term to 0, I'm going to leave the anisotropic version and just set the other term to 0 whenever I want, which is this first case. Okay, so here in this line of code, I write the equations. As you can see, these are exactly the equations that you studied yesterday. And so I'm going to just run it. Actually, I should quit the kernel just for you to make sure that this is really working. Otherwise, you may not believe me. Okay. So yeah, this is, well, I like to do this sort of modular, but so I'm putting everything inside of this variable here. And then now we have the equations in our code, so we just need the equation of state. Again, typically you write the equation of state, well, typically I mean a lot of times you see the equation of state written as pressure as a function of the energy density. Again, I want to really stress that it's not the most general way to write it. Typically what you do is to write the form for energy density in terms of some other microphysical variables, like, for example, the mass density or the number density of particles, depending on what you want to do. And, well, then use thermodynamics relations to obtain the pressure from that. And this is sort of what we have here. So this is the, for example, the polytropic form for the, well, for the equation of state. This actually was something that was in the slides in the first lecture. Well, this is just a constant density equation of state, and this is for constant sound speed equation of state. So then you can choose whatever you want to study. I'm putting here these 3 examples so that when I make this available for you, you can use them, but you can put whatever other equation of state that you want. The tabulated equations of state are a bit more complicated. They require to change a bit the code, but it's still very easy to do, and sort of the highlight will be the same. This does not matter really. This is just another way to put everything in short form. So I'm choosing here to study the polytropic equation of state as as an example. And then I'm just setting here some variables that I will need for the code. And then, well, basically the pressures are obtained from the energy density. In the case of a fluid, I'm saying that the tangential pressure is equal to the radial pressure, because that's the case of a fluid. The isotropic fluid, I should emphasize. And then I just need to run this code, because the radial pressure, I'm writing this expression here. This comes from thermodynamics. And now I'll run this. And in principle now, if I do a consistency check, I should have the expressions for it. And yep, we have it. So the energy density, I have this expression here, which are what I wrote initially. And the two pressures are the same, and the anisotropy is 0. And this is what we sort of known for the polytropic equation of state. Pressure is basically a power law of the energy density. Okay, now we go through the numerical part, and this is sort of what I want to really stress. This is very easy to do. So what we need to do, again, I sort of give a list of points that we need to do, right? We need to integrate the equation from the center, so we need to specify some boundary conditions at the center of star. Integrate outwards, eventually you will hit the surface. This surface condition is when the pressure vanishes, and I will show how we can do that very easily also with Mathematica. But in principle, of course, we could just set for example, saying that the energy density is a constant at the center. Well, turns out that that's not very good for Mathematica to find the solution, and actually the best procedure is to do sort of an expansion of the solution close to the center. So that's what I do in these models here. So basically, so let's take our equations again. I'm here putting basically replacing the density, the pressures by the equation of state that I have. This is what I do here. It's not needed for this step, but to illustrate and make it easier is what I chose to do. So this is what you get for the equations, the TOV equations after you replace with the equations of state. And now I do sort of a Taylor expansion around the center. Now these coefficients, sometimes if the equations that you have are very complicated, you may have tried to guess it. Here I'm putting the coefficients that are, that I already know that are non-zero. Well, there are some that are 0, but the first ones are non-zero. But you can do that a bit with trial and error if you don't want to sort of expand in your head all the equations. And so let's run it. So now I have these Taylor expansions. I'll put here just to do the replacement. And now I will expand the equations close to the center. And let me show you what will be probably the output. So I will get something like this. So several terms that will be expansions in R. For example, this term will be expanded in R squared. This will be in R cubed, etc. Then you'll have the equation for the potential here, which will also be, for example, you have this constant term, a term with R, etc., etc. So let me close this again. So I want to highlight that you need to be very careful with the number of terms that you put, because otherwise, let me give you an example here. If you're not careful and you want to solve and you don't put enough terms, there will be some of these equations that you want to solve, for example, that won't be very useful and will give you bad results, because simply they would be solved for higher order terms that you are not putting there. So we need to be very careful with that. Here I'm sort of solving that. So what I do is, well, I multiply each of the equations by an appropriate power of R in order to do everything automatically. But let me just stress that you could in principle solve each equation by hand, but I like my codes, well, very short and clean. So that's why I'm choosing to do this. But sometimes if I'm being lazy to think, which is something that I don't recommend, but if I'm being very lazy, I'll just solve it individually and my code will become a mess. But that's why for you I'm showing you the clean version. But I'm sure you understand. Okay, so we expand here. Then this is just to obtain the coefficients. Now this other line is just to put all the coefficients equal to 0, but because in the end we want to put all the coefficients equal to 0. Again, these are the variables that we need to solve for. I should emphasize that when you do this, well, you don't have any equations. So let me show you the result that I have after this. Whoops. You don't have any equation. Well, for example, you see this equation here is for this term mc3, which is sort of the third power in the mass expansion, but you don't have any equation, for example, for the phi c at 0 and for the rho c 0. That makes sense because, well, the potential at the center and the density at the center are free parameters that you need to impose in your model to build the star. Well, the potential is a different story that I will explain later. Okay, so these are the variables that you need to solve for. We do that. We tell our Mathematica to solve for, and then that's it. These are the sort of the coefficients of our expansion at the center that we'll use to construct our numerical integrator. Well, to build our numerical integrator. And so this is just putting them in a nice variable. And so now the final step is the integrator, of course. I like to build a function for that. And so this function that I called here fluid integrator takes as input, well, the central value for the potential, that is something that we need to provide, the central value for the mass density, which is another free parameter that you need. Again, different values of this central density will give you stars with different mass and radius. And then there are the parameters for your equation of state. So basically the n and the polytropic scale factor, the k. And finally, you need to also to give your integrator that, well, some bounds. You need to integrate between something and something. In general, you should not put 0 in your code, because the computer will just say that it's blowing up. So you need to put a very small number. So that's why I have here this parameter that represents the radius at the center. Okay. Now I'm just assigning this to some variables. There's nothing fancy here, just to make the code a bit cleaner and to be sort of used by in other cases. These are just the equations, and I'm just replacing with the parameters that I'm providing. Same thing for the boundary conditions. I'm just putting the variables that I need to solve for, which are these 3. And now it's the other thing that is important, the stopping condition. Luckily, Mathematica has this very nice function, which is the when event, which basically allows you to do something when a certain event is reached. In this case, I'm just saying, well, stop our integrator when the pressure is 0. In our case, well, we cannot put really 0, because if the integrator goes to negative values, then the equations will become a mess. So we just stop at a very small value. Now, particularly for fluids, this does not work very well, because this method of when event is very particular. I don't remember exactly why, but turns out that if you multiply both sides by the energy density, no. Well, it also works, but in this case, by the baryonic density, which you sort of could take out, it becomes very well. But this is just, well, Mathematica being Mathematica. And then when this condition is reached, so basically when the pressure becomes smaller than 10 to minus 12, I normally use 10 to minus 15, you do this. In this case, this is the code for stopping integration. So let me run here. The rest is just doing the end solve, and then you play with the working precision, accuracy goal, etc. as you want. It's not needed to be this high. And so, well, this is it. So now I run here. I forgot to run the units because I sort of quit the kernel after had done this. Okay, so this is it. Now, for example, I'm starting with a central density of 10 to the 15 grams per centimeter cube, which is sort of the densities typical for a neutron star. You run it. I'll give some errors because this thing here has less precision than the one that I put in the differential, in the numerical integrator, but we could take it out. And now we have the solutions. For example, if I put here this, which is what I call the solutions, we have the form for the mass, the potential, and then, well, the density, the pressures, everything else that I put there, and that is basically everything that we need for our system. Let me be quick running through this. For example, now we can start the radius and the star very easily. So the radius will be the last point that we have in our integrator. So again, because we are stopping the integration at the radius, this limit here will be the radius of our star. And it sort of makes even sense for a neutron star because this is sort of the order of 10 kilometers. This is a bit smaller, but this is because of, well, this is already a bit high density. And so that's what I'm doing here. And then the mass, you just, well, take the mass function, put it at that value, and that's it. There's nothing special there. And then, for example, you can see the compactness. In this case, okay, we get this value for this compactness of this neutron star. Then, okay, I'm not going to do this here. I can put the code also available for that part if you want, but then you can construct these curves of mass radius diagram, but the idea is just you repeat this for a lot of densities. Okay, last question. I had here the central value for the potential, of course. I did not specify what I did there. In fact, I just put 1, but there's a trick that you need to do. For example, if you see basically what happens to the GTT component of the metric from the interior, you basically get y. Yeah, this is. Sorry. You get this value here, and now if you match it from the exterior, you have a different value, and you want to match it with the Schwarzschild solution outside. So it means that our central value of the potential was wrong. Luckily, you don't need to do a shooting method for that, because luckily this sort of equation decouples from the other ones. You can sort of do a rescaling of your parameter using this sort of expression here. This is very easy to show analytically. That needs to be this expression here, your rescaling. And then you just need to add this parameter to the value that you add. So basically, you need to integrate twice in order to match it. This is wrong. This is 15. Okay. For some reason, this is. I think something went wrong here. This. Sorry, I modified the code yesterday night. Okay, so now I'm going to ask you to believe me that this will work, because I don't want to debug it, because I still want to tell some things. So I'll just move to the case of elastic stars where it's working, and show you that. So the idea is really the same. I'm not going to go through the details again, but for example, I start here with the equation of state of a very simple polytropic form, which basically is the one that we had before, plus this quadratic correction. And then I'm going to run everything very quickly for you to see that is working. Density, blah, blah, blah. Okay, I'm not going to do the consistency check. So these are the equations. Now, when we go to elastic stars, I want to emphasize again that we have a new variable that we need to solve for, this eta that I mentioned yesterday. Luckily, as I've said, this eta is given in terms of delta. So actually you can append, well, I showed you the integral form, but you can write it in a differential form that you can solve at the same time with the other equations, which is this equation here. And so I also want the boundary conditions for that, which is what I'm doing here. And this will be, now I'm going to go a bit faster, so just to show you that in only a few minutes, we can get a solution for an elastic star, an ultra-compact elastic star, that is very easy to obtain. Basically, you are just doing ND-solve in Mathematica. okay, these were the boundary conditions, I'm going to trust that it's okay. The elastic integrator is exactly the same. I did not do anything else except that I don't need to do this trick that was here, because for some reason, magically, if it's not a fluid, this when event works. Now, I've run it, and let me see if this is working. Yep, perfectly. So, okay, don't spoil, let me put a lower density. So you see that you have this sort of, at lower densities, you sort of the radius at the order of the radius of a neutron star. But for these ultra compact objects, if you keep increasing the density, whoops, no, 54, no. Let's not become overly dramatic. You start decreasing the radius, which will mean eventually, if you compute this exactly as the same as before, this radius and mass, you get higher compactness, and eventually, let me put here, for example, 17, which is very, very high even for a neutron star. Oops. You are approaching the compactness of black holes. So here, again, here we're already at 0.43. If you keep increasing the density, we'll approach the compactness of a black hole. If you increase this other parameter of the equation of state, this epsilon, the scale of the elasticity, this will go even faster. So this is it. This is very easy to do. You can do then very nice figures. When I give you this code, I want to make, well, everything available, so I'll also give you the routines for the plots, everything that I use. And so let me go back to the presentation, if I can. Okay. So I hope I sort of motivated that this is very easy to do in practice, and it's even more easy than, well, sort of the theory that was behind. So now I'll go to what I really wanted to do in the last part of this 3-course lecture, which is sort of giving you some idea of what are the phenomenology for these models of exotic compact objects that I just talked about, that you can use to really, well, probe for their existence or to try to constrain them. And now, how do I click the slide? Yep. So we have several different tests that you can do. I'm going to focus on tests with gravitational waves. I'm not going to talk about electromagnetic tests, but this was, well, was already mentioned here in this workshop. I think Carlos mentioned about the tests with the shadows and the lensing. And so the idea is that you can do several independent tests actually for the same signal of gravitational wave, depending on the phase, on the region of the gravitational wave that you want to look. For example, you know that in the early stages of the gravitational signal, the two objects are doing an in-spiral. Here I'm focusing, of course, on signals of compact object binaries. And in this in-spiral phase, there are several things that are important, well, several characteristics of the compact objects that are important. One is the multiple moments, which are basically, well, what is the shape of the compact object. Other one is tidal heating, and this is a bit more complicated, but it has to do with the fact that the horizon sort of is an absorption surface, while the radius does not absorb that much. And then we have these tidal deformations, which is sort of kind of analogous to the multiple moments, but it's the effect on the deformation of the body caused by the other companion object. And you can do tests of the nature of these objects with each of these 3 points that I've just mentioned. Then if you go, well, you let these two objects merge. In the merger, it's a mess to do tests, because you need to only understand this signal through numerical relativity that Miguel was just talking about. But then you can go to the post-merger, where things become a bit more simple to study analytically, and then you can, for example, look at quasi-normal modes and gravitational echoes. And I'm going to talk briefly about this. So I'll start, well, in the opposite way. I'll start from the merger outwards. So this is sort of what I just mentioned. In the post-merger phase, basically two objects just end up colliding. They are in this very energetic event, and they want to relax towards this final stationary configuration. So if you wait, well, a bit after this event, in order to dissipate most of this big big energy, you basically can describe your compact object as the final stationary object that is rotating, for example, your Kerr black hole, plus some perturbation on top that is time dependent. Now, if you do the math, you will see that this perturbation is governed by an equation of this type that is in the bottom, this the second derivative of the field, the second time derivative of the field, of a master function, let's say, plus some second derivative of the sort of the tortoise coordinate. And then there's this potential term that is there. And this potential will depend on the type of perturbation. For example, if it's polar axial sector, it does not matter really the details for this presentation here. I just want to emphasize there are two types. But the important thing now is let's think that we write a time-independent version of that. We obtain something that looks like the time-independent Schrodinger equation, where we have the frequency of the mode there, the AWGAM. And now if we look, here actually on the right we have the shape of this potential that I've just mentioned before. And now we can think about this problem as the problem of sort of a string that is attached to two boundaries, and we can compute this eigenvalue problem. Now for a string, this will give you some normal modes. In the case of a black hole, this will give you what are the quasi-normal modes, because, this is a dissipative system. Now, what are the boundary conditions that we need to impose to solve this problem? Well, for a black hole, it's very easy. There's an horizon. So at horizon, everything is going in. There's nothing coming out from the horizon. That's obvious. And then at infinity, you just want outgoing waves. If you think about an exotic compact object, it's sort of the opposite, not opposite, but it's different. Because now you have a surface, and you can have ingoing and outgoing waves at the surface. So you already have some difference in the boundary condition. But infinity, you impose the same. You only want outgoing waves at infinity. Now, for black holes, you can compute these quasi-normal modes, and they have very interesting properties. For example, one of them is this isospectrality between the axial and polar modes. But other things that I want to highlight here that are important is that, for example, this imaginary part of the quasi-normal modes becomes larger with this n. So n represents sort of the overtones. For example, if you have a rope, you can also have these overtones of the vibration of the rope. So it's one mode, two modes, etc. If you want to do, you can play with the rope and see. And so what this means is that sort of higher overtones have a quick damping time. So in the end, basically all this sort of ring down of your compact object is mostly dominated by the leading mode. Now we can see what happens for exotic compact object. You can compute these quasi-normal modes. And the first thing that we see is that, the isospectrality breaks. So there's not the same curve for axial and polar modes. And there's even other thing, is that in the black hole limit, the quasi-normal modes have low frequencies and are very long-lived. So it's not exactly sort of the opposite as the black hole. So in the figure you can see that because the black hole is sort of that dot that is in the upper right part of the figure, and these are the curves for the exotic compact objects. And as you go towards the black hole limit, actually you are going farther away from that black dot that we have there. And so that's a very interesting way to see the differences. Now, we can look at a time-dependent version of this problem. And so this is sort of what we'll do if we have a perturbation that is interacting with sort of this maximum of the potential. This will sort of split into two contributions. So imagine that you have a wave that sort of interacts with this maximum. It will split in two parts. One part goes inwards towards, it will be either the surface or an horizon, depending on the object. And another part will be reflected immediately towards infinity. And if this is horizon, what goes in is absorbed. And that's the end of the story. So if you are very far away looking at the signal, this is what you'll see. You'll see basically this prompt ring down. And the values that I have here are basically the sort of basically the time scales and the frequency associated with the dominant quasi-normal mode. Now we can ask the same thing, but for an exotic compact object, what will happen, right? We've just seen that for a black hole, the ingoing wave is absorbed. For echo, sort of I mentioned before when I talked about quasi-normal modes, we'll have two types of things. We'll have waves that are going in and waves that are going out, because basically these will bounce between the surface and the potential. So if we do, well, I'm going to call it simulation, but it's just, again, a numerical integrated. This is what we'll see, and this is what we hope to observe. So each time that the perturbation interacts with the potential, it splits in two parts. One is reflected, one is transmitted. And each time it hits the surface, it's sort of reflected back. So here I'm considering a perfectly reflective surface. And this perfect reflective surface basically has this potential wall at the surface that basically reflects all the perturbation. Now, if you are at infinity, this is what we'll see, something like this. So for the black hole, I don't know if you can see, sort of the dashed black line is like the figure that we had before. But now for an exotic compact object, you'll see sort of this repeated signal that will appear periodically after the first prompt ring down. But now if you look at really the left part, you see that the signal for the black hole and the red curve are really overlapped. You can ask why, because, well, the quasi-normal modes were sort of different. Well, the thing is that this first part of the signal actually does not carry any information about the surface, right? Because this is the sort of, you send a wave, and the wave is hitting the photosphere, and, well, it is reflecting back. So basically only understands that there's a photosphere there. To get really to the surface, you need to wait for basically the wave to hit the surface. And actually the quasi-normal modes are basically will start to appear in the sort of shape of those echoes when n goes to infinity. So the number of echoes goes to infinity. Okay, now we can. So this was a model for, let's say, a very stiff exotic compact object, so that had a wall at the surface. We can see, for example, for one of these stars. And one thing that we'll see is that the perturbation will take much more time traveling within the object, so within the matter of the object, than outside. So what is the consequence of that? Is that, for example, if you do exactly this sort of simulation for the echoes, so above we had what we just saw. So you see more or less that, again, I should mention what that epsilon is in the upper plot, this 10 to minus 15, but basically it just says that the surface is basically 10 to minus 15 away from the horizon. So you see a very compact object. Here on the bottom, I have sort of the stars that I've mentioned yesterday, and I have here, for example, let's look at the red curve. This is what I call unphysical because some of it has some sound speeds larger than 1, but this does not matter for this case. The point is that this particular object has a compactness that is much lower than the one above, like say 10 to the 0.44 or something. And you see that the echo timescale is already at 500. This is because exactly what I just mentioned. Most of the time when you have a sort of a star, this perturbation takes a lot of time traveling through the matter within the star, and is just not, well, basically hitting the surface and coming back. Okay, this is sort of one of the main key features that you can look for, so the quasi-normal modes and the echoes. I want to go very briefly in these last 10 minutes or 5 minutes to some other features, for example, multiple moments and tidal effects. So multiple moments, I think you probably know it from Newtonian gravity. These are sort of coefficients that tells you basically the deviation on the potential of your body from the spherical symmetric, the potential of a spherical symmetric body. These are represented by these MLs that are in the expression on the left. In general relativity, things are a bit more complicated, but they're sort of a similar definition if you are in some specific system of coordinates. I don't want to go into those details here. But the key point is that black holes have this no-hair theorem, right? So basically, everything is given in terms of the mass and the angular momentum. Well, black holes in GR that are uncharged. And particularly, if you look at the multipolar structure, it has this very elegant form that is written on the left, which sort of implies that the black holes are axisymmetric and equatorially symmetric. But exotic compact objects, well, do not need to be like that. Actually, they can have some deviations for these multiple moments. And I think as you've seen from the talk of Zeus yesterday, when you have deviations from symmetry, you can have, well, quite a lot of interesting things. And this is sort of what you can probe with multiple moments. So for example, there are sort of types of exotic compact objects like fuzzballs that have these deformed structures, and they have different multiple moments than from black holes. Then recall the talk of Etevaldo and Carlos Herrero about multipolar boson stars and prolate Broca stars. This sort of highlights how important it is also to study these multiple moments. Now I'm going to skip a bit these last slides because I want to go here to this part, because these sort of multiple moments appear at 2pn order in a gravitational wave expansion. So this is an expression in, well, sort of powers of the velocity. And although we had some detection so far, we are not able to measure these multiple moments because they are very correlated with the spin. We have not measured accurately the spin so far. But the good thing is that, well, in the future when LISA flies, this extreme mass ratio in spirals, so in spirals of an object with, well, basically a very big mass and a lighter compact object around it, will be very good to constrain a lot of these multiple moments. And actually, if you look at the sort of the leading multiple moment that you can constrain, this M2, you'll be able to constrain it, let's say, up to 1 part in 10 to the 4, which is, well, a great constraint. So which will possibly be, be able to tell us if we, well, deviations or not from these nowhere properties of black holes. For tidal love numbers, things are very similar. Tidal love numbers are sort of the equivalent of these multiple moments, but for tidal interactions. So how much a body is deformed because of the interaction of a second object, and these are represented by those k's that I have there, in this case k2. And for black holes, these are zeros. So if a black hole, well, is being deformed by another compact object, basically you won't have any love number at all. And this is very intriguing, and it was puzzling until a few years ago. But this is actually very useful and important because it sort of gives you a smoking gun to probe for. Whenever something is zero, it's very easy to probe for something that is different from zero. For example, for neutron stars, just to give a bit of scale, this tidal love number, this K2, is of the order 100. Now, if you look at exotic compact objects that have, well, a smaller compactness, let's say order of a boson star, we have some tidal deformability that can be sort of also the order 100. But if you approach this compactness of black hole, this tidal love number will probably go to zero. But the question is how? And well, we found out a few years ago that for these sort of hard or sort of artificial exotic compact objects, it goes logarithmically to zero, which is, well, sort of very interesting, this property, because it will sort of gives you an idea that you can probe Planckian corrections to the horizon, because if this goes logarithmically, if you are sort of like 10 to the minus 33 centimeters away from the horizon, the tidal deformability will be of the order of 10 to minus 2. And this is something that we probably can measure with LISA also. But this is only for this is only valid for those very artificial and sort of hard exotic compact objects. If you take, for example, these anisotropic stars or these elastic stars that I mentioned, which are sort of have an interior region, this logarithmically vanishing that was sort of essential for these sort of probes will vanish, and actually it will go polynomially, which means that, for example, if you want to probe things 10 to the minus 33 centimeters away from the horizon, this idle of number will be sort of the order 10 to minus 33 also. So it will be completely difficult to probe. And so I'm going to wrap up here. So let me just mention how this enters in the waveform. Basically, well, I've mentioned this PN expansion before for the multiple moments. Here is sort of the same thing, but the first leading term will appear at 5 PN order, so it's something that is a bit harder to test. And the key point is that, in any case, with future gravitational wave detectors, we will be able to probe it. So, especially for, well, highly spin binaries. And this is something that we are currently looking for. So I think I'm running out of time, so I want to end up here and just want to say some final words. So I think it's a wonderful time for you to be studying this field of exotic compact objects. In a few years, we'll have a lot of experiments to detect gravitational waves, to detect electromagnetic signals of compact objects, and I think we'll probably have quite a lot of detections that will give us a lot of data, and understanding the nature of basically the signals that we are seeing will be essential. And for that, it's essential to know how to model them and how to correctly describe them, and also what sort of signals they can give us. And so this is why this sort of research is important, and I think is something that, well, I hope that you follow along these lines in your careers. And I think that's it for me. I hope you enjoy the course, and I'll be around if you have any questions also now, if you have any questions. So thank you.
Thank you, Guilherme. Well, do you have it? There are any questions or comments?
Well, thank you very much for the presentation. In the very beginning of it, you showed your notebook. If you can come back to it. Yeah, I think it's the cell 76. Yeah, but it's in the end of it. It wasn't on the point that you were computing the running. Yes, this one. You write a when event line and explain something about why this is different from the previous case, but I didn't understood it, so I would like you to explain again, please.
So okay, I'll try to recall if what I once saw about why this was not so. Okay, let me give you the ad hoc explanation, and it will be, well, so in principle you just want to do this, right? So you want the pressure to be small, well, close to zero at least. So this is what you would like to do. Now, if you plug this and put in the case of the fluids that I have above, what you see is that it will integrate everything, but so the pressure will go to zero, and then it will go up, down, and you won't find exactly the first zero, basically. Now, at some point in my life, I remember trying to understand why. I think this is because, so if you expand this expression of the pressure, it's sort of quadratic in the baryonic density, or the variable that you want to find. And for some reason, this method that mathematics uses cannot find quadratic expressions very well. So what I did was, well, I multiplied the pressure by the baryonic density and multiplied the other side by the baryonic density, such that it cancels out in principle. And magic happens, it works. So it was sort of a trial and error until it works. So in principle, you don't need to do that. So if you start to play with this number, well, and the precisions mathematical will end up finding the solution. but I found out the other trick was easier, and I did not have to worry about playing with precisions and thresholds. It just works. Yeah. Rob?
Any further question or comments? No? Well, I'd like to thank Guilherme for his real nice short course. It was short, but it was really enjoyable. And in the name of the organizing committee, thank you, Guilherme. So please let's thank Guilherme again.